Hi, everyone. Oh, sorry, I had a little bit of a technical glitch there for a second where it told me we couldn't stream, and that was a little scary. But I am here now. Everything looks like it's working. And please let me know in the chat window if you can hear me okay, if you can see me okay. That would be great, just to confirm that everything is working properly. Um, I am Dr. Danielle Snowflack. You may remember me from the past live streams that we've done here on the Edvotek YouTube page. And I am the Senior Director of Education at Edvotek. We are again here to have a biotech live stream. Today we're going to be talking about vaping and the ways that we can use laboratory techniques to analyze the e-liquids that are used in vaping, and we would and the applications of this, and I really like this topic for the lab because it's not only going to let us talk about the chemistry of molecules, the way that thin layer chromatography is performed, but it's going to allow us to bring some public health issues in as well. So, we're glad to have you here today. And this is going to be, again, our last live stream of the year. We've done 14 of these, believe it or not. It's crazy, but thank you, for joining us, and let's get started. So for those of you who have not joined us previously, we are Edvotek, the biotechnology education company. We were founded over 30 years ago by a professor of biotechnology at Georgetown, Dr. Jack Trixian. As a researcher, he knew of everything that was going on in the biotechnology lab. And this was a time of great innovation. So a lot of the modern molecular daily were developed during this time. But very little of this was being translated to the classroom. And so, that was really the genesis of Edvotek. So how can we inspire and engage students by using what was happening in real labs around the world every day? And not only that, though, we really wanted to, make sure that the equipment in the reagents we were selling were real, authentic equipment and experiments, so that the students were doing what the researchers were doing and using equipment that was just as durable and just as just as durable, just as precise and reliable as laboratory equipment, but designed with the student in mind. And so Edvotek largely focuses in the education sphere, where we work with educators all over the world to demystify science and to foster the next generation hands-on learning activities. So today we are going to focus on thin layer chromatography, which is a technique that we can use to separate molecules based on their physical properties. And so this is a really important process for many types of industrial research and development, including biomedical and pharmaceutical research, and which we'll discuss some of the applications in this workshop. The experiment we're running today is Kit 211, which is going to focus on analyzing simulated vaping e-liquids using thin layer chromatography. In choosing this chromatography experiment, we are choosing an experiment that is a natural mix of STEM concepts. This experiment uses brightly colored dyes that we're going to separate using chromatography based on their physical properties. A mathematics extension involves measuring the distance that each of these dyes travels and calculating the retention factor, which is a measure of how the buffer, the dyes, and the matrix work together to separate our molecules, again, based on their physical properties. And so using this information, we identify specific molecules in a complex mixture. While this technique we're doing today is very powerful, it is also easy enough to do in the classroom laboratory or even in your basement, like I'm doing it today and like I've been doing for the past couple months, for these experiments. So we are recording this demonstration and we will post it on our YouTube page. The slides will be available on our website. If you'd like to be notified when they're posted, please fill out the form that Maria has linked to in the chat box, please, and we will send you the link to the slides. We are also offering professional development certificates for those people who attend live. So be sure to check off that box if you want a certificate. The link is only going to be live for an hour after the presentation, so be sure to complete it before 5 p.m. Eastern Standard Time. And one thing before we really get started is that I do want to mention that until December 31st, 2020, we are, ringing out the new year with our Cyber Week specials. You can check them out online at edvotek.com. A lot of our best-selling laboratory equipment is on sale right now. And so if you're looking to outfit your lab, if you want to upgrade some of your components, or if you're just interested in getting involved with something really new and fantastic like our personal PCR machine, there are lots of fantastic pieces of equipment on sale right now, so be sure to check it out. Maria, if you can put the link in the chat box in case anybody wants to check out what we're offering, that would be great. But we have a lot of stuff we're very proud of. So let's get started with our discussion. I think one thing that we know is that, smoking kills. The connection between smoking cigarettes and life-threatening conditions like heart disease, stroke, and lung cancer are clear and well known. But the problem is right now we don't yet know the link between e-cigarettes and vaping and health conditions. So here the messages are mixed. Sometimes e-cigarettes are presented as a safer alternative to traditional tobacco products. And other times vaping is described as an alarming and dangerous new trend that's creating a next generation of nicotine users. So people who are addicted to a stimulant substance. And so we don't know whether this will cause lasting damage to people's lungs and their bodies. So let's talk a little bit more about what vaping is, what chemicals are involved, and how researchers can evaluate the effects of vaping in the short and long term. So e-cigarettes come in countless shapes and sizes, and they go by many different names, including vapes, tanks, or ends, or electronic nicotine delivery systems. And in the graphic on this page, I have we've pulled a bunch of the most common vapes, pictures of them from the internet and placed them here. And they look very different. Each of them look very different, but, at the base level, they all have the same basic construction. There's a chamber to hold the liquid, a heating element like a coil, battery, or microprocessor, and a mouthpiece. And together, these parts heat solutions called e-liquids to the point where it creates a smoke-like mist. When we think of this as a vapor, it's actually more accurately an aerosol, so a suspension of solid and liquid particles in a gas. Many times, not many times, all the times, users are going to breathe in this aerosol in order to deliver a potent dose of nicotine or other chemicals. Sorry, I was just trying to get my water bottle out of the way. I almost knocked it over. Anyway, I didn't realize I was going so far off screen. So you can get a potent dose of nicotine or flavor or other chemicals or drugs. Some users choose to consume nicotine-free e-liquids for the flavors, or to purchase kind of off-market e-liquids that can contain additional drugs or intoxicants. So when chemical analysis is performed, oftentimes researchers will find around 100 chemical components found in these e-liquids, including the flavorants, the nicotine, and other drugs. Several of these substances are capable of causing cancer in living tissues and are categorized as carcinogens. So those are chemicals that will cause cancer either in culture or in animals or in people. Several others are going to be classified as irritants because they can cause inflammation in our bodies, or they can be considered as poisons because they can cause injury or death at high doses. So the popularity of vaping is growing right now in many demographics, and that can be problematic. In recent years, the popularity of vaping has grown exponentially. Originally, this was promoted as a way for tobacco consumers to quit smoking. It's kind of a transition, almost like nicotine gum or a patch, something to kind of get you away from smoking cigarettes, where, in addition to some of the chemicals you're ingesting, you're also ingesting the smoke and the byproducts from the actual combustion of the leaves. It was thought that this might be a cleaner, safer way to, taper off of smoking. However, today we're finding that many vapors have never used anything but like e-cigarettes and these e-liquids. So it's actually becoming a problem in itself, as an addictive, delivery system for nicotine. And so while vaping is generally considered to be less harmful than smoking cigarettes, it is still not considered safe to use or to inhale it secondhand. Unfortunately, right now, there are huge gaps in what we currently know about safety and the long-term effects of vaping. But what I can say is that there are studies that are starting to show that as vaping becomes more common and as more people are partaking in vaping for extended periods of time, there are health risks. And the image on this slide is going to show some of those health risks. And one thing you can have your students do is to look further into some of these health risks. I'm really going to talk about one that was in the news, two that have been in the news recently. The first is that, there are cases of these e-cigarette ends units exploding if not used properly. They are an electronic combustion system. And, if something goes wrong, the unit can explode, and that would cause bodily injury, burns, abrasions. If you had it in your pocket, that could affect your legs. If you were smoking it at the time, you could have burns to your lungs, to your mouth. And so that is one problem there. The second is going to be, and most of the health concerns come to the chemical components that are present in the e-liquid. This is going to include solvents like propylene glycol, drugs like nicotine, and contaminants like heavy metals, which are often found in off-market or homemade e-liquids, as well as a range of flavors, preservatives, and aromatic transporters. And so these additives are going to vary tremendously between different brands and different types of e-liquids, but most are going to, in general, if you get a commercially available e-liquid, the compounds are going to be food safe, so they're going to meet food quality standards. However, the high heat of the vaping, device used to create the aerosol can actually cause changes in these chemicals or cause them to react with one another to create new compounds that might not be food safe. Also, the health effects of a lot of these chemicals are different based on whether you're ingesting them. So if you're eating them versus inhaling them through, and absorbing them through your lungs. And so consequently, the ingredients that are labeled as safe for consumption can still be dangerous when aerosolized and inhaled. Consequently, a striking example of this happened in 2019, where there was an outbreak of severe lung infection in young and otherwise healthy individuals. So mostly young people who did not have any pre-existing conditions, no comorbidities, no pre-existing lung problems. It was epidemic. It was an incredibly large number of people who were having this related illness all around the same time. And so a common denominator in all of these individuals is that they were vapors. So all of them were using e-cigarettes regularly. And what investigators found is that in the vape liquid, there was a chemical called vitamin E acetate, which is a derivative of a naturally occurring chemical, vitamin E. And they found this in the lungs of sick people, but not in the lungs of healthy individuals. And so this additive is used safely every day in nutritional supplements and in skin creams. So this is something that's generally regarded as safe. It had not really shown toxicity or any other sort of health issue. But when it was added to these, off-market e-liquids as a safe thickener, it severely damaged the user's lungs and caused them to experience shortness of breath and chest pains. And so this is an example of something that we generally consider to be safe. But when it is aerosolized, it was dangerous. And this condition actually caused thousands of hospitalizations and 55 reported deaths. And so I think that one of the things that comes from this is that there's a lot that we really still don't know about vaping, whether it's a safe alternative, or whether there are some chemicals that are more safe to use in this way than others. And as I said before, there are still huge gaps in what we currently know about the safety and long-term health effects of vaping as well. Research are starting to work to narrow these gaps through experiments and clinical tests rather than waiting to observe them in users over years. And some of these health effects might not be obvious in the initial studies. These chronic conditions may only become obvious several years after vaping has begun or as they started. And so what we do know from the data is available is that there are a lot of variables when it comes to vaping and the effects on human health. But what we can quickly and easily analyze are the chemical components within e-liquids, and we can use thin layer chromatography to do that. So if you were with me on a previous chromatography webinar, you may recognize this slide, but I really like to talk about this to kind of give a framework for what chromatography is and the history of chromatography, because chromatography is a very diverse set of techniques, but they all use to separate molecules by their physical and chemical properties. The word chromatography is from the Greek chroma and graphene, which roughly translates to color writing. And a fun fact is that the botanist Mikhail Tzvet, who ran the first real chromatography experiment, named the technique after himself. So his last name in Russian translates to color. So by using the Greek chroma, which also means color, he may have been naming the technique after himself. So I think that's pretty cool, pretty fun fact that may come up in a trivia contest one day. But the precursors of today's chromatography can be traced back to the mid-19th century, where researchers were analyzing the pigments found in plants. And so in these experiments, scientists mixed the pigments with solvents and spotted them onto filter paper. As the pigments traveled through the paper, they separated into distinct pools, creating bands with different colors, on the paper. And so in the very early 20th century, Tzvet applied the principles of paper separation to plant pigments to column chromatography. So calcium carbonate was carefully packed into a column and used to separate pigments instead of paper. Furthermore, he realized that the solvent used for chromatography was also important. Certain molecules would separate better with polar solvents than nonpolar and vice versa. In the mid-1900s, as we kind of see in this picture, the technique expanded to include many different types of separation. There is ion exchange chromatography, where it separates molecules based by their charge. There is size exclusion chromatography, which is also known as gel filtration chromatography. Oh, I went one too far. Which is going to separate molecules so size exclusion or gel filtration separates molecules based on their apparent size. And what you can see here is an example of one of our size exclusion experiments. There is affinity chromatography. Some of my pictures got a little messed up here because I'll just say that we do have affinity chromatography, which is going to use protein binding interactions to separate molecules. And then there's also thin layer chromatography, which you can see on this picture, which is what we're going to be doing today. And I'll abbreviate thin layer chromatography as TLC throughout the workshop. And I'll use them interchangeably. All right, so I'm going to turn over to my camera setup so that you can see all of the components as I do the work. So let me get my gloves on, because I want to show you what you need to do this experiment. And it's all like what you can see, it's a very simple setup. I just have the reagents of the kit in a couple glass jars and bottles. So the first thing that we need, one of the more important reagents, is going to be these. These are our thin layer chromatography plates, or our TLC plates. And this plate is a very thin, you can see it's difficult for me to just pick it up. It's very thin, and it's actually plastic. It looks like paper, under this light, but it's a thin piece of plastic, and it is coated with a matrix. In this case, it is cellulose, which is a polar molecule, which will become important later. This matrix is going to capture the molecules that pass up through, that are drawn up through this matrix based on their chemical properties. We're using two different solvent systems in this experiment. We're using one that is going to be more polar than the other, and that will become important as we discuss the molecules and the nature of thin layer chromatography. They are a mixture of buffers and compounds that move our samples through the TLC matrix. They can be polar or nonpolar, which influence our results. And then we have our sample mixtures. In this case, they are dyes that are going to simulate our e-liquids. We have 3 samples here, and then we have a control. And one thing that I really like about the e-liquids in this experiment is, even though they are simulated, they are not for vaping use. But one thing that we did do is we scented all of them with different odorants. So this one is banana. It has a very strong banana scent. You can see on the tube it's labeled Banana Blast. But what you can do is you'll aliquot these for your students to perform the experiment. They can sniff to determine which vape liquid that they have and write that in their notebook. It's kind of adding a fun and more authentic element to this experiment. So these dyes, as I said, are simulating our e-liquids, and you can see they're all kind of a bluey, a greenish color. And just by looking at them, we can't tell whether this is one molecule or 2 or 3 or however many dyes are going to come together to make this color. And we're going to use the physical differences of these molecules to separate them. And each of these different colored dyes are going to represent a different fluids. And so we're going to use in the buffer. There are a few ways we can do this. One is a plastic transfer pipette, which I'm going to be using today. And then the other is going to be a transfer pipette. It's going to be an adjustable volume micropipette. And so we can run this experiment without any sort of special equipment. And I'm going to be performing these in our glass jars. Oop, I just got a message on my phone that was blocking my camera. All right, so I can see this here. I've got my case jars. And so chromatography techniques, like what we're going to be doing today, they are going to separate molecules based on their physical properties. In this case, it's going to be whether the molecules are polar or nonpolar. In thin layer chromatography, we have a stationary phase, which is on our plate, and the mobile phase, which is going to be in our solvent system, which is in the beaker, and that's a liquid. Our TLC plate is covered with their matrix. This matrix is going to be used to separate the molecules into different pools or bands. Our buffer solutions are the mobile phase, and they flow through this matrix by capillary action. The applied sample, which we're going to spot on this plate here, move back a little so it comes in more, developed by our stationary phase. And that means that the molecules in the sample that are carried for the flow of the buffer through the matrix, where they're going to be gradually separated. The separated zones of molecules are then visualized to let us know and identify which chemical components are present in the mixture. Flip the plate, it brings the dyes with it. More soluble dyes travel up the paper with the solvent. Insoluble dyes stay at the bottom of the plate or move more slowly. And the solubility depends on the solvent. And the movement also depends on the interactions of the molecules with this matrix. Actually, you can see I chipped a little bit of the matrix off right there accidentally. It is a little fragile, so you want your students to be more careful than I was. But you can see that it's a clear plastic sheet, of the sheet right there. And then you have this dull matte matrix, a thin layer of it on the other side. And that's the matrix that's going to do the separation. And so today we're actually using 2 different solvent systems. So we'll be able to see the effects of polarity on our molecules as we're separating them. All right, so using chromatography to separate our molecules. So let's define some key terms. Vocabulary is always important with these experiments. On the TLC plates, we are going to have spots once they're developed. And these are partially or completely separated zones of molecules that are seen on our TLC plate. each molecule travels, and a lot of this is illustrated in the graphic on the slide, which you can get if you request the slides in the form. But what you can see is that, you know, each molecule is going to travel a distance through the plate from the origin. So that's our line here. So we have to keep track of where we spot our molecules. Because they are going to move through the plate as they're moved through with solvent. The distance the solvent travels from the bottom to the top of the plate is called the solvent front. And the distance that the molecules travel from the origin and the solvent front are actually important numbers that are going to be critical for us to calculate something called the retention factor, which is going to allow us to distinguish between the chemicals present in our simulated e-liquids. All right. So how do we prepare? So we are going to prepare. I've already started doing some of the work preparing the TLC plate. They come as a big sheet, and you're going to separate them into smaller pieces. So this is 4 centimeters by 5 centimeters. It's pretty small. And what you'll notice is that I did draw on my origin line, my baseline, and I have 4 little dots for our 4 samples. And I wrote this in pencil, and that's important to note that it's pencil and not pen, because just remember, pen is made out of ink, and ink will separate in our system, right? Because ink is made of dyes that are suspended in a liquid or a gel, and that's how we can write using the pen. If we do make a mark with the pen, you will separate that by TLC. The second thing is you kind of want to use a dull pencil because your pencil can scratch through this matrix layer, and we want to make sure we keep that layer intact when we're doing the experiment to have it so that we do not break the area where the solvent can be drawn up through the plate. Let's see. So we have them in a rectangle. And so now we're going to transfer our samples onto our plates using a pipette. I'm going to set up the plates the same way for both of them so that we can compare the results directly. So first I'm going to use our control. And so when I'm pipetting these liquids, especially these very small volumes of liquids, I don't actually use the pipette bulb. I actually like to use the stem of the pipette. I like to squeeze the stem of the pipette. And this is going to allow us to have more precision in making our drops, because we only want to have the barest drop here because we want to get good resolution between all of our different chemicals. And so what you can see is I just have a tiny spot of our control here and here. That's our control. I am going to dispose of these pipettes between samples. If you would like to, you wash them out with water between to rinse out the dyes. You know, we don't want the dyes or the odorants to go between the samples because that would be cross-contamination. And, you know, like you do want to emphasize that with your students. It's good lab technique to make sure that they are properly cleaning between their different samples. But, you know, if they happen to cross-contaminate something or get wrong results, that's actually a really great teaching moment. You know, mistakes happen all the time in lab. It's one of the reasons why we repeat experiments to make sure that we did them correctly. But, you know, it's just nice to emphasize, oh, you see that dot is a little too big. We'll see how that turns out, though. You know, that's okay. You know, science is messy. We are humans doing science, and, you know, there are, you know, we are limited by our, you know, memory, which is why we need to keep good lab notebooks to keep our records of what we're doing. You know, we're limited by our hand skills, you know, and there's a lot of different things that go into the process of science. And so, you know, everyone can do science, everyone can do these experiments. But, you know, it's good to keep a record of what you're doing so that if you do make mistakes, you know where the mistake was and what you would do differently the next time. And that's really important too. because most times, when you're doing an experiment and you're trying something the first time, it doesn't necessarily work as you were expecting. And that's a scientific method. You have a hypothesis, you try an experiment, you see how it turns out. And if it doesn't turn out the way you thought it was, you revise your hypothesis and create a new experiment and see how it goes. All right, so I have these samples spotted, and you can see each of them has a different smell. This one is clove. It's very strong. I can smell that. There's clove, vanilla, and cinnamon. They all smell different. And you can see they all have similar colors, kind of blues and greens. And your students are going to use these, the students are going to develop these plates to determine which are the different chemicals present. So we're going to let these dry for a little bit. So let's talk a little bit about the chemistry of what's going on. All right. So a molecule's bonds are going to determine the polarity of the molecule. And so thin layer chromatography is particularly sensitive to small differences in the structure and polarity of different chemicals. Structural features include molecular weights, geometry, and carbon-carbon double bonds. These physical traits are going to influence how easily a molecule migrates through the stationary phase. Polarity describes molecules that have subareas of positive and negative charge. And this occurs when one nucleus in a molecule attracts the negatively charged electron more strongly than the other nuclei. And so what you can see here in this image is a visual representation of polar bonds. And those are the bonds between two different ions. And what we can see in molecules where the charge of the nuclei are similar, we can see that we have a nonpolar bond. So each nucleus is going to pull on the electrons in the same way, and we don't have any regions of negatives or positives. In the polar molecule, in contrast, we can see, in this case, we're looking at an HCl. We can see that the chloride ion is drawing the electrons much more strongly than the hydrogen, thus creating a partial negative and a partial positive. In polar molecules, again, they share equally. One part of the molecule is more positive, one part is more negative, creating poles. Molecules are water-loving. And if you look at the top of this diagram, see is that we have the directionality, the charge of some of these bonds. So you can see the more positive side, which is represented by the little cross on the end of the arrow, and the arrowhead is going to be the more negative portion. Now, in contrast, nonpolar molecules do share electrons equally. No part of them are no poles, and we call these hydrophobic or water-fearing molecules. And in general, they're not going to be soluble. So the polarity of the molecules allow them to mix with water, because water itself is a polar molecule with a partial negative and a partial positive charge on its different atoms. And those partial positives and the partial negatives like to interact with one another. So our TLC is going to separate our molecules based on their physical properties. And as I mentioned, our plates are coated with an absorbent material, in this case cellulose. And the polarity of this molecule directly influences our results when we separate the molecules using TLC, because the molecules are going to interact differently with the matrix based on their properties. The stationary phases used in TLC experiments are often a mixture of neutral molecules, polar molecules, and even more strongly charged ionic compounds. These molecules interact with the polar molecules in a sample and slow their rate of migration. And so in our case, the matrix that we're using on our TLC plate is a cellulose, which is a polar molecule. We spotted our e-liquid on the control plate at the origin. And again, you can see here. We spotted it at the origin. Some of my spots are bigger than others. We'll see how the results are. You will get tighter bands with the smaller dots, but it's still worth trying and, explaining why our results may or may not be as good as they could be. So we are going to take this, we place it into the solvent, which moves our samples through our adsorbent matrix. The more polar molecules stick to the matrix more than the nonpolar molecules. And the nature of the solvent influences the mixture through the matrix, which we'll talk about shortly. Okay. So our next step is to start getting things started. So I am going to pour our different solvents into our jars. So I'm going to put our potassium acetate into this jar. So this is an aqueous potassium acetate solution. And this solution is going to be more polar. I need to put a little more in here. You want to have a thin layer. You want to kind of just coat the bottom. It goes in, but it does not go over the samples. Because I'm not making careful measurements. You know, my samples might be a little too high or too low, but that actually looks pretty good. So I'm going to kind of rest this over here to start our experiment. All right, so this is our potassium acetate. I'm just going to write that here. This is component F. Make label on my table. And then here we have component E. Now this is our sodium citrate isopropanol mixture. And this is going to be a less polar solvent. And so we're going to see the difference between a more polar and a less polar solvent and the effects on the separation. And you can see, I hope you can see, let me bring this even a little closer, is how quickly oh, dang. Well, that didn't work out exactly right because my plate fell over when we were moving it. Luckily, I have another one that we can use. I'm not going to be as careful with my markings, because we don't necessarily have the time. But again, this is experimental error, right? This is what happens when you're not being careful in the laboratory. And so, we always want to take care when moving our different experiments. Bad things can happen. Let's not call it bad. Let's just get accidents. They're just scientific accidents, which is why we always do repeat our experiments to make sure that our results are in fact accurate and reproducible. And reproducibility is important in research because phenomena are authentic. And I'm very carefully trying to work around my camera, which kind of gets in the way. But I want you all to see what I'm doing. And I think it's important for your students to see accidents happen. So if they're watching this video, no judgment here. Accidents happen. Just write it in your lab notebook and try again. Now, where's my last sample? D. All right. So I'm going to put this last sample in. I'm going to very carefully put my sample into here. Hopefully I spotted them high enough so that they don't immediately dissolve. Yep, okay. And now we can move on. Okay, so in here I've got my two buffer systems. My one is sodium citrate, an isopropyl alcohol, and this is going to be less polar than our aqueous potassium acetate one, and the alcohol is a less polar molecule than water. Our TLC sheet so that the bottom is touching the solvent. And then we're going to allow the solvent to be drawn up through our TLC plates, which is going to move our dye molecules. And this is going to happen quickly, so you can see how quickly it is happening in real time. Before they even get to the point where they're running the samples is to have them form a hypothesis of which chemicals are in the sample and write that down. Your students should research the components that are present in the e-liquids to see their effects on human health. And some of these molecules, their chemistry, and to determine why they migrate the way they do through the gel. And so again, as you remember, we started with molecules that were all similar color. And what we can see is that we're getting combinations, and we're seeing different movement based on our different buffer systems. And so again, that's reinforcing the fact that all of these molecules have a different polarity to them, a different charge, which interacts both with the cellulose the cellulose matrix and the different solvents to be separated. So we talked a little bit about the TLC matrix. And in this case, the matrix is the same on both of these sheets, so it's going to interact with the molecules in a similar way. Variable here. And again, this is going to affect our migration differently based on the chemistry of our dye molecules in solution, our simulated vaping liquid. And so polarity directly affects the solubility of these molecules because polar substances dissolve better in polar solvents and nonpolar are better in nonpolar solvents. And by selecting different mobile and stationary phases, we can isolate a wide range of chemicals. And some combinations are going to be better than others. That we have a polar buffer and we have a nonpolar buffer. So, and then we have a mixture of the two. And we can see that when we use either of the pure solutions, so either the purely nonpolar, the hexane, or the purely polar, which is the ethyl acetate, we don't get good separation between our molecules. What we need to do is have a mixture that is partially polar and partially nonpolar by mixing our ethyl acetate and our hexane. And that gives us a combination that allows us to clearly separate all of our different molecules by size or by their chemical components. And so it's a little bit like Goldilocks, you don't want to be too hot or too cold results. So the nature of the solvent and the matrix together is going to influence the separation of your mixture. These plates out, and I'm going to make a pencil line right here on the top, our dye front. And I'm pushing a little too hard, so it is going to stir up our matrix. We're already done, but I'm just going to mark off that solvent front. Let me see if I can do this on camera. So you can see I'm holding it at a weird angle and I'm not pressing lightly enough. But I'm marking off the distance that traveled. All right, and we're going to let these dry out a little bit before we do our analysis. So let me bring... and we're going to let those dry. Compounds are spotted on our TLC plate and placed into a solvent. They are going to separate with the solvent as it travels up the plate or by adhering to the plate and not traveling with the solvent. And different solvents and different plate polymers can give different results by TLC. Sample molecules will have a stationary and mobile phases depending on their structure. Samples that have little or no solubility in the mobile phase, but high solubility in the stationary phase will migrate. If we're looking at one of our results, those here, let me pick up this one. Those are going to be the molecules down here, right? So those are the ones that are going to interact and not interact with our mobile phase, our buffers, very well. Conversely, samples that have little solubility in the stationary phase but are highly soluble, just migration rates. And so these are going to be ones that move very quickly up through with our buffer as it travels through our TLC matrix. Where mathematics comes into play is that the retention factor is the ratio of the distance that the solute traveled. So those are going to be our dye molecules in relation to the distance that the solvent traveled. So when the experiment is finished, we calculate these values for the different dyes and it helps us analyze our results. So TLC is commonly used in all different kinds of labs. Some examples are clinical, pharmaceutical, food, or cosmetic laboratories. And they use TLC to identify compounds and mixtures. So there are diagnostic tests used in the medical field that use TLC to determine, whether a compound is present. Forensic scientists will use TLC to determine, whether compounds are present. And food and cosmetic laboratories often use TLC to determine the purity of their colorants, their odorants, their dyes, to make sure that they are chemically pure before we go to manufacture. Another place that researchers use TLC in the laboratory is to assay the completeness of chemical reactions. So you could imagine if we have a reaction that has multiple steps, we're going to have multiple different, partial products present in our solution, and we want to make sure that chemical reaction goes from start to finish as much as possible. So we want the greatest possible yield. So what you could imagine is we spot our starting products and our purified product onto a plate, along with our reaction with our reaction that's happening. And using TLC, we'll be able to see the proportion of starting materials, intermediates, and final products that we have using the gel based on the different bands that we see using TLC. And when coupled with spectroscopy, TLC can actually identify specific components. So what you would do is you would spot, this is what we see in the figure up top. You're going to spot your chemicals on the TLC plate, separate them using the different buffer system, visualize the location, and then use spectroscopy to determine, what's present in your different spots. So that's actually a way you can determine if a particular spot on your plate is a pure chemical or a mixture and what's available in that mixture. So let's analyze our results. So here are our, lab results that were done in the lab, and we'll take a look at ours too. So the first that we're going to look at is here, and I cut off which buffer was used in which when I put this figure together. So that's my bad. I will fix it in the slide that I will distribute. But if we're kind of roughly looking at the pattern, what we can see is that this one looks like it is probably the bottom one. And so that's our potassium acetate. And we can see that, we have one dye that adhered strongly with the matrix and did not interact well with our solvent. So it did not travel through. These yellow and kind of greenish molecules are intermediate. And then this bright blue traveled all the way to the top with the solvent front. And so to calculate the RF, what we do is we measure the distance that the solvent traveled and the distance that the molecules traveled. And then we use those two numbers to calculate the RF. So again, this was our aqueous solution. This is the potassium acetate. And so very high, more polar molecules are going to travel with the buffer more quickly than less polar molecules. Conversely, here we have our sodium citrate isopropyl alcohol, which is going to be our more polar buffer. And we can see that our molecules travel differently. So we can see the blues look different where they traveled. So we have this band here, which not only is a different color, but it's going to be in a different spot. And again, that is based on its interactions with the matrix and with the buffer. So, each is going to be slightly more or less soluble and interactive with either the stationary phase or the mobile phase based on their chemistry, and they move through here. And so again, it's important to let your students know that, all of these different vaping liquids are mixtures of chemicals. Each of the chemicals has chemical properties, and they're going to interact with human health differently. Again, something that could be safe when you ingest it might be unsafe when you are going to vape it, when it's combusted in the e-cigarette, and when it's inhaled into your lungs. And so what I hope you're, and so your students will identify which molecules are present and how they move differently based on the solvent. And so what I hope that we've learned today is that, TLC is a very versatile technique that we can use for properties. And one of the reasons it's so versatile is because we can get different results just by changing the buffer. And this is going to tell us a lot about the physical and chemical properties of our molecules. I think when it comes to the public health area, having your students do the research and learn more about vaping, about the chemicals that are present in cigarette cartridges, it's important to have them research to realize that there is not a lot of information on human health yet, and the consequences there. But also to look at, they can research there. They could also look at, the way that scientists learned about smoking and the effects that smoking has on the body, because those are going to be comparable in terms of the type of research and development that needs to be done. This is a fun, visual, colorful experiment that can be done really quickly. If you're sending experiments home with your students, you could even break this up and have your students do it at home, snap a photo of the results, and then, upload them to your e-learning portal to analyze the results that way. And so with that, we are we are wrapping up. If you would like the slides, again, please be sure to click the link. In the professional development certificate, please be sure to click the link. And we will send that to you as soon as possible. Please do not forget that this is our Cyber Month, so we are running specials through the end of the month. And, we are just so glad that you have spent these live streams with us, doing some science, and we look forward to seeing you in the new year. So please have a happy and safe holiday season, happy and healthy new year, and I look forward to seeing you all again in January. So have a fantastic day. If there are any questions, ask them now. We are always available at info@edvotek.com or try one of our social media channels. And we really look forward to helping you get biotech into your classroom. Again, wishing everybody a happy and healthy holiday season and a fantastic new year. We're all looking forward to a fantastic 2021. Have a great day, and thank you so much for joining us.